I want you to do something for just a second. Like, look around at whatever device you are using right now to listen to this. Maybe it is a smartphone resting in your hand, or, maybe a laptop sitting on a desk. Or perhaps you are wearing a pair of wireless headphones.
Right, yeah.
Whatever it is, that device is powered by this totally invisible, silent force. It is a force that ancient humans quite literally thought was magic. We completely take it for granted today, right up until the exact moment the power goes out and we are just left fumbling in the dark.
Oh, absolutely. It is the ultimate modern paradox, really. We are utterly dependent on something we cannot even see. And for the most part, we rarely think about the underlying physics of how it operates until, that screen goes black.
Yeah, exactly. That is why today we are embarking on a comprehensive deep dive into the source material on electricity. We are pulling from a massive, highly detailed Wikipedia article to really get to the body of this. The mission of this deep dive is to peel back that mundane, everyday utility. We want to stop looking at electricity as just the thing that charges your phone and reveal it for what it truly is, like a staggering and absolutely fundamental force of the universe.
And we should establish from the outset that electricity is not a human invention. We didn't engineer it in a laboratory somewhere. It is literally the very language of the natural world.
Right.
I mean, it governed how matter held together billions of years before we even existed. Our historical journey with electricity is simply a story of observation, realization, and eventually harnessing a mechanism that was already running the cosmos.
So before humans could ever dream of manipulating that mechanism, we could only feel it. And I mean that biologically. According to the source text, our first encounters with electricity were very visceral.
Visceral is a good word for it, yeah.
Ancient Egyptian texts dating all the way back to 2750 BCE actually describe certain electric fish as the protectors of all other fish.
Which makes sense, because they lacked the vocabulary to describe an electric shock in scientific terms. When a fisherman waded into the Nile, and his leg inexplicably went numb, they naturally attributed that defensive mechanism to a magical or divine property.
Oh, wow, yeah. So they really thought it was magic.
Right, but they were actually interacting with specialized organs in these fish. These organs use stacked cells called electrocytes to discharge a sudden, synchronized wave of ions.
Okay, let's unpack this. The source mentions that ancient Greek and Roman physicians, people like Pliny the Elder and Scribonius Largus, actually began utilizing this biological shock for medical treatments.
Yeah, that is a wild detail.
They would direct patients suffering from gout or brutal headaches to touch an electric catfish or an electric ray. They knew the shock had a numbing effect, essentially prescribing a powerful live jolt to cure severe ailments.
They were basically engaging in primitive electrotherapy. They recognized the physiological effect, like the way an external charge overwrote the pain signals in the human nervous system.
Even though they had absolutely no idea what it actually was.
Exactly. They had no idea what the underlying mechanism was at all. And they were simultaneously observing another manifestation of this same force through friction.
Right. We have the classic amber experiment. So the Greek philosopher Thales of Miletus, around 600 BCE, noticed that if he rubbed cat fur on a piece of amber, the amber would suddenly start attracting light objects.
Like feathers and things like that.
Yeah, feathers. So Thales rubbing amber was basically the ancient equivalent of shuffling your socks on a carpet just to shock your sibling.
But they didn't know it was static electricity, right?
No, they didn't. Thales miscategorized the phenomenon entirely. He believed the friction was actually rendering the amber magnetic.
Oh, interesting.
Yeah, he compared it to magnetite, which is a naturally magnetic mineral that does not need to be rubbed to attract iron. He just assumed he was dealing with the exact same force, but activated differently.
And that misunderstanding lasted for an incredibly long time. It wasn't until the year 1600 that an English scientist named William Gilbert finally studied the phenomenon carefully.
Yes, almost 2,000 years later. Right, and he proved that this static effect was completely distinct from the magnetic lodestone effect. He even coined a new Neo-Latin word for it, electricus.
Which is derived from electron, the Greek word for amber. So for millennia, electricity was treated either as an isolated biological curiosity in the Nile or just a strange parlor trick involving tree resin.
Wow.
It was completely disconnected from the fundamental forces of physics.
Yeah.
The very word we use for the backbone of modern civilization literally translates to, well, like amber.
Moving from rooting fur to the invisible structure of the universe is a massive leap. We know now that this isn't just an amber quirk. To understand why those shocks happen, we have to look at the subatomic structure.
Right. We have to look at the atoms themselves.
The carriers of this electric charge are protons carrying a positive charge and electrons carrying a negative charge.
And the interaction between those charges is dictated by Coulomb's law. It is a fundamental rule. Opposite charges attract, so a positive and a negative will pull together, and like charges repel.
So two negatives will push apart, and two positives will push apart.
Exactly. And the force with which they push or pull is the electromagnetic force.
The source material has a statistic comparing that electromagnetic force to gravity, and it honestly broke my brain a little bit.
It is staggering, I know.
If you take two electrons and place them next to each other, they experience a gravitational attraction pulling them together because they both have mass.
Because everything with mass has gravity.
Right. But they also experience an electromagnetic repulsion pushing them apart because they both have a negative charge. The text says the electromagnetic force pushing them apart is 10 to the 42nd power times stronger than the gravitational attraction pulling them together.
Yeah.
That is a 1 with 42 zeros after it.
It really highlights that at the subatomic scale, gravity is essentially a rounding error. I mean, the electric force just completely overwhelms it.
Here's where it gets really interesting. Wait, if the electrical force is a staggering 10 to the 42nd power times stronger than gravity, why don't I just repel off the surface of the Earth and float away into space?
If we connect this to the bigger picture, the answer actually lies in the concept of neutrality.
Neutrality.
Yeah, think about it like this. Gravity only has one mode. It attracts. It is purely additive. The larger the mass, the stronger the combined pull.
Okay, that makes sense.
But electricity, however, comes in two opposing flavors, positive and negative. At the macroscopic scale, so planets, stars, even your own body, matter generally carries an equal number of positive protons and negative electrons.
Oh, I see. So the massive attractive and repulsive forces are perfectly balanced. They just cancel each other out over long distances.
Exactly. Because those electrical fields cancel out, gravity, despite being unbelievably weak, becomes the dominant force at the scale of planets and galaxies.
Wow.
But inside the atom, that overwhelming electromagnetic force binds electrons to nuclei and atoms to other atoms. Without this staggering balance of opposing charges, the physical structure of matter itself just wouldn't hold together.
So we have this raw, overwhelming power sitting inside all matter, constantly canceling itself out. And for centuries, humanity could only occasionally scrape off a tiny chaotic spark of it through friction.
Right, just little static shocks.
Until Benjamin Franklin's 1752 kite experiment, that proved that the massive power of lightning in the sky was fundamentally the exact same electrical phenomenon as the spark you get from rubbing amber.
And Franklin also worked heavily with Leyden jars. These were early devices used for storing large amounts of static charge.
How did those work exactly?
Well, you would generate a charge through friction, store the imbalance of electrons in the glass jar, and then release it all at once in a massive, instantaneous spark.
Just a big zap.
Exactly. It was useful for experiments, but it was just a burst. You cannot run a machine on a single violent spark.
So how did we finally manage to make it flow continuously? Because that seems like the real game changer.
The paradigm shift occurred in 1800. This was thanks to Alessandro Volta and the invention of the first battery, known as the voltaic pile.
Ah, Volta. Hence the volt.
Right. Volta stacked alternating discs of zinc and copper, separating them with cloth or cardboard soaked in salt water.
I'm trying to picture the chemistry there. Why does stacking different wet metals create a flow of electricity?
It creates an electrochemical gradient. Basically, the zinc wants to oxidize, meaning it wants to give up electrons, and the copper wants to reduce, so it wants to gain electrons.
Okay.
But those electrons cannot easily travel directly through the saltwater barrier. So if you connect a wire from the top zinc disk to the bottom copper disk, you provide a pathway.
Oh, I get it. The electrons flow through the wire to get from the zinc to the copper?
Exactly. That creates a steady, continuous current, while the salt water allows ions to move and balance the charge inside the pile.
It is like humanity went from trying to awkwardly catch lightning in a bucket, literally with those Leyden jars, to finally inventing the plumbing needed for a steady, reliable stream of water. Volta gave us the pipes.
That is a perfect analogy, yes.
And having that steady current running through a wire led to one of the most serendipitous discoveries in scientific history. In 1820, a physicist named Hans Christian Ørsted was giving a lecture.
Right, the Comtes experiment.
Yes. He had a wire hooked up to a battery, and he noticed something strange happen to a nearby magnetic compass.
Every time he switched the continuous current on, The compass needle twitched. He realized that an electric current actively generates a magnetic field around it as it moves.
Bringing those two ancient observations, the rubbing of the amber and the magnetic lodestone, together into one unified phenomenon.
To build on your plumbing analogy, Ørsted's twitching compass needle was the moment humanity realized this electrical water wasn't just flowing. The pipes themselves were radiating a magnetic field.
Which is wild to think about.
It really is. That realization unlocked the true potential of the Industrial Revolution because it provided the mechanism to turn electrical flow into actual physical motion.
So to build those machines, engineers had to map out the rules of how this invisible water actually moves through the plumbing. The source breaks down fundamental concepts we hear all the time, like voltage and current.
Right. Terms we use every day.
If we stick to the water analogy, electric potential, which we commonly call voltage, is basically the water pressure. It is a measure of the work required to move a charge between 2 points.
Yes. A higher voltage means a stronger push forcing the electrons through the wire.
And current, measured in amperes, is the actual volume of the flow itself. It measures how many charged particles are moving past a specific point per second.
Exactly. But the source material drops a historical bombshell here about that flow.
Oh yeah, the Benjamin Franklin thing.
Right. When Franklin was doing his early work with glass rods, he basically had to guess which way the invisible charge was flowing.
And he guessed wrong.
He did. He decided that the charge was positive and that it flowed from positive to negative. And he established a convention that the entire scientific world adopted for circuit diagrams.
But the actual physical particles moving through a wire are the electrons, and they carry a negative charge. They are physically flowing in the exact opposite direction, from negative to positive.
Yep, exactly backwards.
So, what does this all mean? Hold on, you are telling me Ben Franklin guessed wrong about which way the particles were moving, and electrical engineers for centuries have just been pretending it flows backwards rather than fixing the diagrams? That must be a nightmare for physics students.
What is fascinating here is that the physical reality of the electron's movement doesn't actually invalidate the mathematics.
Really? How is that possible?
Well, because of how electric circuits are structured mathematically, pretending a positive charge flows one way yields the exact same numerical result as a negative charge flowing the other way. The equations just work perfectly either way.
That is incredibly lucky.
It is. Rather than rewrite every single textbook and redesign every schematic after the electron was finally discovered in 1897, the scientific community just kept Franklin's convention.
Talk about human historical quirks becoming baked into universal, rigorous sciences. It works, even if it is completely backwards.
Absolutely. Now, another crucial rule of the road is resistance, which is measured in ohms.
Right, resistance. Because as those electrons push through a material, they don't have a perfectly clear path. They are constantly colliding with the atoms of the conductor.
And those collisions create friction. That friction dissipates the electrical energy as heat. This is known as Joule heating.
Which wasn't just an annoyance for early engineers to minimize. It was actually a physical property they could exploit.
Oh, definitely.
Like if you push enough current through a very thin wire with a high resistance, those collisions generate so much heat that the wire literally glows brightly.
Which is the fundamental mechanism of the incandescent light bulb.
Exactly. We forced electrons to violently push their way through a resistive tungsten filament, and we used the resulting friction to conquer the dark.
Mastering those circuit dynamics allowed humanity to rapidly scale electricity from a scientific novelty to the absolute backbone of modern society. Once we understood how to generate a steady current, the applications just exploded.
Yeah, like in 1821, right after Ørsted discovered that moving electricity creates magnetism, Michael Faraday decided to see if he could invite that relationship.
And he created the homopolar motor.
The physical setup described in the text for this is wild. He took a permanent magnet, stuck it upright in a pool of liquid mercury, which, by the way, is highly conductive and incredibly toxic.
It's extremely toxic.
And he dangled a wire into the mercury. When he ran a current through the wire, the magnetic field radiating from the current interacted with the permanent magnet.
And the interaction of those two magnetic fields creates a physical push, which is known as the Lorentz force. The wire experienced a continuous force that caused it to circle around the magnet without stopping.
Wow.
It was the first time electrical energy had been continuously converted into mechanical energy. Faraday basically gave us the birth of the electric motor.
And then 10 years later, in 1831, Faraday reversed his own process. He found that if you physically move a piece of metal through a magnetic field, the magnetic force, literally pushes the electrons down the wire.
inducing an electrical current.
Yeah, that was the first electrical generator. A spinning wire in a pool of toxic mercury sounds like a weird parlor trick, but it is fundamentally the grandfather of every electric vehicle motor and massive wind turbine we use today.
We literally just spin magnets inside coils of wire to push electrons into our homes.
It is so beautifully simple when you break it down like that.
But the scaling didn't stop at heavy machinery and giant turbines. The deep dive reveals how electricity transitioned from moving massive physical objects to moving microscopic packets of information. We shifted into the era of solid-state electronics.
Right. The text highlights Albert Einstein's 1905 paper on the photoelectric effect. He proved that light acts as discrete packets of energy, or photons, that can strike a material and physically knock electrons loose from their atoms.
Which is a huge deal.
Yeah, that exact subatomic mechanism is the entire basis for the solar panels we use today to generate power from the sun.
And Einstein's work laid the groundwork for quantum mechanics. That gave engineers a much deeper understanding of how electrons behave inside different solid materials.
They realized they didn't just have to push electrons through copper wires.
Right. They realized they could manipulate them inside crystalline structures. That realization culminated in 1947 at Bell Labs, when John Bardeen and Walter Brattain invented the point contact transistor.
Because up until that point, computing relied on massive, really fragile vacuum tubes. They were essentially modified light bulbs that used immense heat to boil electrons off a filament to control electrical flow.
They burned out constantly and generated massive amounts of heat.
And they literally attracted moths, which is actually where we get the term computer bug.
Yeah, that is a great piece of trivia. The transistor replaced all of that with a solid piece of semiconductor material, like germanium or silicon.
And by doping the silicon, basically introducing tiny amounts of impurities like phosphorus or boron, engineers could alter the atomic structure.
Right, to create areas with extra electrons and areas with missing electrons, which are called holes. By sandwiching those materials together, you create a gate where a tiny input current can control a massive output current.
So you can turn the flow of electricity on and off digitally, millions of times a second, with absolutely no moving parts and very little heat.
The transistor made it possible to shrink room-sized computers down to microchips. It is arguably the single most important invention of the 20th century.
Mastering the flow of electricity at the microscopic level completely made the digital age possible.
Absolutely.
And the cultural perception of this force has just undergone a massive whiplash. In the late 18th and early 19th centuries, electricity was viewed with absolute awe, bordering on witchcraft.
It terrified people.
The text points to Mary Shelley's Frankenstein from 1818. She was deeply inspired by the work of Luigi Galvani, a scientist who discovered that applying an electrical spark to the dissected legs of dead frogs made the muscles twitch violently.
Galvani had stumbled upon bioelectromagnetics. He demonstrated that biological nervous systems run on electrical impulses.
But to the public, however, applying a spark to dead tissue and seeing it move looked exactly like raising the dead.
Right. Early masters of the grid, like Thomas Edison or Nikola Tesla, were popularly viewed as wielding wizard-like powers. They were commanding an invisible force that animated flesh and illuminated entire cities.
We went from viewing electricity as a terrifying magical force capable of reanimating corpses to a completely boring utility.
A very boring utility, yeah.
The source notes the irony that today we only ever pay attention to electricity when it stops flowing. We went from being terrified of wizards to just being profoundly annoyed that our laptop battery's at 2%.
We have successfully integrated this violent cosmic force into the invisible background of our daily routines. It governs our modern world just as silently as it governs the atomic structure of the universe.
Well, just to recap the terrain we have covered today on this deep dive into the source material. We started with ancient fishermen experiencing biological shocks in the Nile.
We moved to Thales misidentifying amber, to Benjamin Franklin mapping the storm clouds, and Volta building the first chemical battery.
And we traced the physical Lorentz force of Faraday's Hodor all the way to the billions of microscopic solid-state transistors sitting quietly in the pocket of you, the listener, right now.
It is a remarkable trajectory. But before we conclude, there's one final mind-bending mechanism from the source material worth lingering on.
Oh, yeah.
We've discussed generating electricity through chemical reactions in batteries or by spinning magnets inside coils. But there is a phenomenon known as piezoelectricity.
I am still trying to wrap my head around this one. It is so weird.
It is. Certain everyday, highly structured crystals have a unique asymmetric atomic lattice.
Okay.
If you take a piece of quartz or even a simple crystal of sugar, and you physically apply pressure to it, like if you just squeeze it, the mechanical stress physically deforms that atomic lattice.
Wait, really? Squeezing it?
Yes, that deformation literally forces the positive and negative charges inside the crystal to separate.
Meaning the simple act of mechanical pressure generates an actual electrical voltage across the crystal.
Precisely.
Next time you bite down on a piece of rock candy or look at the face of a quartz watch, remember, you aren't just looking at inert matter. You are literally squeezing an imbalance of electrons into existence.
It is incredible.
The magic isn't just humming in the massive high-voltage lines strung across the highway. It is woven into the very crystalline fabric of the world around you, just waiting for a push.
This really raises an important question about what other invisible forces we are constantly interacting with, completely unaware of their true nature.
Absolutely. Well, thank you for joining us on this deep dive into the source material. Look down at that device in your hand one more time, and hopefully the invisible force powering it feels just a little bit more magical.